Water heater control system simulation in LabView. There is a water heater that should keep the water at the constant temperature of 70 degrees Celsius. The water heater consists of insulated tank, the water, and the heating element. Initial water temperature is 20 Celsius, and our task is to simulate water heater behavior. So first, let's build the simulation model in QuickField. I start QuickField and create the new problem. The problem name is the tank heater, and the folder is this one. The problem type is transient heat transfer. The model class is axisymmetric. This model class is suitable to model cylindrical bodies. Length units are centimeters. Click Next. For transient problems, we should specify the integration time and the time step. Well, let the integration time be 2 hours and the time step 1 minute. Yes, and the initial temperature is 20 degrees Celsius. Okay. Here you can see the geometry model editor window. The axis of rotation symmetry is a horizontal one. So in the model, we should draw only the upper half of the cross section. I will use the Insert Shape tool and I will insert the rectangle. The width of the rectangle is 0.6 and the height is 0.3 meters. Oh, we have the units of centimeters, so 60 and 30 here. The insulation thickness is 4 centimeters. So the next rectangle will be located here, 4 centimeters, shifted to the right. Height is 26 centimeters, and the width is 52 centimeters. Okay. Now I will draw the heating element. Switch to the Insert mode and click and draw the lines. Next, we should assign labels to the objects. Through these labels, we will later assign physical properties. I switch to Select mode, click the object to select it, and open the Properties window. Here I should type in the label name. This is the heater. Okay. This is the water. Okay. And this is the insulation. Okay. And we have the boundary. You should hold the Ctrl button pressed to select multiple objects. So these edges I will label as boundary. Now let's assign physical properties. Double-click the label to open the dialog. For the heater, I specify thermal conductivity of 100, heat capacity of 100, and the density of 6000. It is just some piece of metal. For the insulation, double click, I specify thermal conductivity of 0.1, heat capacity of 1000, and the density is 800. For the water, thermal conductivity is 0.6, heat capacity is 4200, and the density is 1000. Okay. On the external surface, the tank is in contact with the air, so I can specify the convection boundary condition. The air temperature is plus 20 degrees Celsius and the convection coefficient 3. Now let's run the analysis. Well, we have to build the finite element mesh, save all simulation files, and then we can start the simulation. The simulation process is finished and we get the temperature of 20 degrees Celsius. That's because we have not specified power source in the heater. Okay, I will open the label properties. The power of the heater is 2 kilowatts, but I should specify power density. Power divided by the volume. So I will switch back to results, use the contour tool, select the heater element, open the integrals, and here is the volume. Oh, I should switch to meters. View length units meters. Now I can copy this value. Again, open the heater block properties and type in power divided by the volume. That's it. Okay, now let's run the analysis again. And we have the results. The water temperature is above 100 degrees. And we know that the water will evaporate and the tank will explode. QuickField doesn't know about it, but we know that the water temperature should not exceed 100 degrees. Well, let's check the water temperature variation in time. I right-click here and choose the time plot. So, to preserve the tank, we should keep the water temperature below 100 degrees Celsius, and we should limit the heating process by 5,800 seconds. Okay, I go to the problem properties, switch to the timing tab and type in 5,800 seconds. Okay. Yes, we will do the analysis again. Run the analysis. And here we got the result. The temperature is 100 degrees Celsius. Now at this moment of time we should switch off the heating element. To simulate this process, I will create the new problem. Tank heater 1. Again, it will be transient heat transfer problem. Length units are centimeters and the model class is axisymmetric. Next. Okay, let's again set the simulation time to be 2 hours and time step to be 60 seconds, 1 minute. And the initial temperature is, well, in first problem the temperature was distributed uniformly and we can specify the initial temperature for the model, for entire model, to be 20 degrees Celsius. Now the temperature is not distributed uniformly, so we can specify just a single value. We need to build the link from first problem to the second one and export the temperature distribution. To be able to create the link, both problems should share the same geometry model file. So I go back and here I will browse and find the geometry model file that is used by the first problem. Okay. Now I have two problems. The problem where the heater is switched on, or I should, you see, these problems share the same geometry model file, but the data files are different, so I should assign physical properties again for these labels. I will simply move labels from one problem to another. So this problem simulates the heating process. The heater is switched on. And in this problem, the heater will be switched off. I will specify 0 power source value. Now I should create the link. I would like to import temperature distribution from the first problem. So in this problem, I will open the properties, switch to the links tab, specify the link type, temperature field distribution, and specify the problem. I would like to take the temperature distribution from this problem. And I add the link. Well, for the transient problem, we should specify the moment of time. This is the moment of time, 5,800 seconds. Update. Okay. Now we have the link. We get the temperature field from the tank heater problem. Now let's run the analysis. Okay, we have switched off the heating element and simulated 2 hours long thermal process. You see the temperature drops below desired 70 degrees Celsius. Again, I can take a look at the temperature variation in time. So our goal is 70 degrees Celsius, and after about 20 minutes we should again switch on the power source. So I open the problem properties and correct the timing. Now it's 1200 seconds or 20 minutes. Let's run the analysis again. And let's take a look at the temperature distribution that was at the beginning of the process. So it was 100 degrees. And minute after minute the temperature was diminishing. So after 20 minutes the temperature was only 70 degrees Celsius. Now we should switch on the power source again. I should create next problem based on the same geometry model, and in this new problem I will take this temperature distribution as an initial. The heater will be switched on, and again I should run the analysis. When the temperature rises to 100 degrees Celsius, I should switch off the power source again and simulate the next problem. So far we ourselves acted as a control system, manually switching on and off the heater. Now let's build the automatic control system. Before building the control system, let's adjust the problem setup. To limit number of problems in chain, we will build the closed loop of just 2 problems. To make a loop, we should put the reference from the first problem to the second one. Okay, I will open the problem properties, go to the links, temperature field, and put the link to the second problem. Final time 100. Okay. Now we have the closed loop. Second problem links to the first problem, and the first problem links to the second problem. To make our control system agile, we will shorten the simulation time. So in the timing, I will set the calculation time to be only 1 minute with the intermediate time step of 10 seconds. I can run the analysis. Okay, now only 1 minute is simulated. And for this problem the same. Open the problem properties, go to the timing. Only 60 seconds will be simulated. Okay, inside the loop, the state of the power source doesn't change. So we can use the single data file for both problems. So I open the problem properties. And I will use the same data file as in the first problem. So if I change the power source to be 0, Run the cycle again. I will simulate the cooling process. And if we run the cycle again, we will model next 2 minutes of the heating process. Now we can build the control system. The control system will run and count simulation cycles, measure the temperature, and switch on and off the power source. Our heater control system simulation in LabView. We have a front panel and the block diagram. To interact with QuickField, you should put the reference here. So I choose the ref number and automation ref number and put it here. This is the reference to the ActiveX class. Right click, select the class, and here you should search for the QuickField type library. I click Browse. The type library is stored in the same folder as QuickField. So I go to the drive C, program files, Terra Analysis, QuickField 6.3 Student Edition, and this is the type library, activefield.dll. OK. Now you can use all internal QuickField objects. We should start with the application. OK. Now in the block diagram, I will use connectivity ActiveX panel. Add the automation open block and connect it input to the refnum block. Next, I would like to access properties of this object. So I will use the property node and connect its input to the automation block. So we have the QuickField application object, and we can access the properties of this object now. We can take a look at the all opened problems. I would like to get the first problem from the collection of problems. So I will use invoke node, put it here, connect the blocks, and choose the method item. I should also provide the problem index. We have 2 problems. For example, I would like to open the first problem with index 1. Next, I would like to simulate this problem. Again, I add the method and connect its input here. Now let's take a look. You see there is no proper method to run the simulation. That's because we have the wrong object type. When we get the item from the collection, we get in fact 2 objects. Here we see the methods of the iDocument object. iDocument could be a geometry model file or physical properties data file. So I can only close the window or save the file. To get specific iProblem object properties, we should perform object type conversion. Use variant to data block. I will remove this link. This block is used to data type conversion. And here we should provide the type. Again, I will insert the ref number here. Choose the ActiveX class. It should be the problem. Okay. Now I connect the ref number to the type conversion block. Object type changed to the iProblem. Now I can access all methods of the iProblem object. I would like to solve the problem. We should provide the no-wait parameter value. In order to get the temperature, we have to wait for the salting process to complete. So I will set the false for the no wait, which means that we should wait. After the problem is solved, we would like to take a look at the results. So again, I will use ActiveX panel and add next invoke node. Connect it to the same iProblem and choose the Analyze Results. Now let's go to QuickField, close all windows, and let's run this virtual instrument. You see the problem was simulated and the results were loaded. Let's take a look at the already built control system. We have two QuickField problems connected in a loop. Now the power source is switched off and the temperature is 20 degrees Celsius. The geometry model file is shared between these two problems, and we have the common data file too. Each problem simulates a short interval of 60 seconds. So if we run the full cycle, we will simulate two problems and model 2 minutes of real-life process. These are problem files in the folder. This is the geometry model file, and this is the data file, data for heat transfer analysis. I will make the copy of this data file and rename it as tank heater on. I will open this file in QuickField, and for this file I will specify the power density of the heater, which is power 2 kilowatts divided by the volume. So our control system will run and count cycles, measure the temperature at this point, for example, and change the reference to the data file if we need to switch power on or off. Now let's take a look at the already built control system. Tank simulation. Again, I will open the block diagram. We have the goal, the temperature we would like to get. It should be 70 degrees Celsius. "20" is the initial temperature to initialize the feedback. These blocks subtract temperatures and we get the temperature difference between the desired temperature and the actual temperature. Then we have the relay block. If the temperature difference is positive, or in other words, if the measured temperature is lower than the goal temperature, we switch on the power. If the temperature difference is negative, or if the measured temperature is greater than the goal temperature, we should switch the power off. To prevent rapid switching on and off, we allow 5 degrees Celsius bandwidth. That is, if after we have the water heated, we switch the power off. And we will switch it on again if the temperature drops 5 degrees Celsius below the goal temperature. After the relay comes the conversion block. The relay output is 1 or 0, and we need to convert it to Boolean true or false. Then comes the virtual instrument. That is a block that runs the simulation and computes the temperature. And the temperature through the feedback block returns to the subject. And here we have the time plot instrument. Now let's take a look what's inside this virtual instrument. Here we have the sequence of 2 simulation blocks and the measurement block. First, we decide which data file to supply to the problems. It could be data file with the switched off power source or data file with switched on power source. Then we simulate first problem. Then we simulate second problem. And then we measure the temperature. So in the front panel, I should provide the data file name for the switched off state and for the switched on state. Now, as you can see, this data file corresponds to the switched off state, and this data file corresponds to the switched on state. Okay. Now let's take aside the simulation block. Now what happens here? We start QuickField, take all open problems, choose the specific problem from the collection, convert the type from iDocument to the iProblem. Then we will change the reference to the data file. Problem refers to geometry model file, to the data file. There could be a reference to the library file. So we should change the data file. And the data file index is 1. And we provide the data file name. So once we have changed the reference, we save the problem and run the analysis. Then, after the problem is calculated, we run the same segments for the second problem. And after the second problem is simulated, we go to the temperature measurement block. In the temperature measurement block, we start QuickField, open all problems, open the second problem. You see, we do not need to know the temperature in the middle of the cycle. we need to know the temperature at the end of the cycle, so we only measure the temperature in the second problem. So we get the second problem, second document, convert the type from I document to the I problem, open the results. In the results, we use the getLocalValues method, and this method takes the input as the point. So we should provide the coordinates point. We will measure the temperature in this point, and it has the coordinates 30 centimeters and 26 centimeters. Well, it should be 0.3 meters for X, 0.26 meters for Y. So we get all local values in this point, and from these values we extract the temperature. In terms of QuickField, the temperature is a potential. Our control system decides to switch on or switch off the temperature. We run two problems in sequence and then measure the temperature in the desired point in the second problem. Now, before we start the simulation, we should specify the simulation parameters. Remember that each problem simulates 1 minute of the process. So the cycle of two problems simulates 2 minutes of the heating process. And in the LabView, in the simulation loop properties, we should type in the time step of 120 seconds. This should be the fixed time step. It is the initial time step, minimum value of the time step, and the maximum value of the time step. And the final time would be 10 hours. Okay, I will the simulation. You see the initial temperature was 20 degrees Celsius, so the relay immediately switched on the power source. You can see the reference to the data file has changed, and the temperature starts to rise. And we run cycle by cycle and control the temperature. Once the temperature rises above 70 degrees, the relay switches the power off and the water starts to cool down. When the temperature drops below 65 degrees Celsius, the power is switched on again, and then the cycle repeats. Simulation is over. So this way you can build the control system in the LabView that will interact with QuickField. In fact, that was a very simple control system. You can do much more with QuickField Open Programming Interface. You can access and modify geometry model. You can change the data, material properties. You can build contours, calculate the integral values.